Okay, so uh, our first example this week with forces is going to be an inclined plane problem. This is kind of a classic problem with forces, and this is going to be one that is a static problem, which means that the objects involved are at rest or moving with a constant velocity. So on the right hand side here, I have a mass sitting on a plane which is at an incline with an angle theta. The coefficient of static friction between the mass and the incline is mu sub s. And mu sub s is just a dimensionless number that is a measure of how strong the strength of friction is between that mass and the surface of the plane. And what we want to find is the largest angle that will support the mass. And so what I mean by that is you can imagine if the angle is 0, the mass is just going to sit there because it's on the ground. And if the angle is 10 degrees, then the mass might still continue to sit there because of the friction. But we can keep increasing that angle until eventually the mass will slide down the incline in spite of the friction because the amount of force pulling it down the incline will exceed the frictional force. And so what we want to do is determine that largest angle which will support the mass right at the moment when we reach the maximum strength of the static friction force. The name of that angle is called the angle of repose, and this angle determines a lot of interesting things, and in particular it determines the angles at which piles of material will naturally form as they are piled up. And what I mean by that is if you say you have a pile of sand, if you just have a random pile of sand, some of that sand is going to flow off the sides of the pile, and it's going to continue to do so until you have a mound, which is roughly conically shaped. And the angle that this mound makes with the ground will be the angle of repose based on the coefficient of static friction between the material and itself. So that is one example where this actually, you'll see this manifesting itself in nature. So we're going to examine the forces that are acting on this object. And there are three relevant forces acting here. First and foremost would be the force of gravity, right? Because this object is on the Earth. There's a force of gravity with a magnitude of mg. And it points straight down towards the ground. Then there's a normal force, which is perpendicular to the ramp itself, right? So the normal force acts perpendicularly to the surface of the ramp, and it pushes upward on the mass to prevent it from falling through the surface of the ramp. And finally, there is a force of static friction, which points up the ramp to prevent the mass from sliding across the ramp's surface. And so it'll point up and to the right because in the absence of that friction force, the mass would tend to slide down and to the left. And so this friction force is parallel to the surface of the ramp. So we can construct a free body diagram. I need to introduce some coordinates first. So I'm going to introduce some coordinates, and so I need an x-axis and a y-axis. What I'm going to do is I'm going to draw my coordinates so that the x-axis points up the ramp, and the y-axis is perpendicular to the ramp. And the reason that I'm going to do that is so that the y-axis will be parallel to the normal force, and the x-axis will be parallel to the force of static friction. That's going to make the algebra much easier when it comes to solving the systems of equations associated with Newton's first law. You'll notice that I'm drawing my coordinates down here. It doesn't really matter where I draw them because the directions of the forces relative to those coordinates don't really matter in terms of where the coordinate system lies. So I'll go ahead and put the origin down at the base of the ramp, but it doesn't really make a difference in terms of the final answer. Now I can make a free body diagram, and I go ahead and draw my forces relative to those coordinates. And you can see that the force of gravity points into the third quadrant of my coordinate system. And that might look a little bit strange because you know that it points straight downwards. And what's going on though is relative to these coordinates, straight downwards is in the third quadrant of those coordinates. So, it's all relative to the orientation of these coordinates when I'm drawing my free body diagram. Okay. The angle that the force of gravity makes with the negative x-axis is 90 degrees minus theta. And the reason for that is that if I have something straight down and something which is parallel to the surface of the ramp, and this is theta, then this angle will be 90 minus theta. So this is the force of gravity, this is the x-axis, the y-axis, and so 90 minus theta is the angle between the force of gravity and the negative x-axis. Now the logical thing to do at this point is to compute some components. So I need to compute the components for my various forces. The normal force and the force of static friction will be very easy. The normal force just points straight up, which means that its x component is 0. This force of static friction points straight to the right, so his y component is 0. And the horizontal, since this force is completely horizontal, the x component just is himself, and it points to the right. And this guy's y component just is his own magnitude, and it points up. The force of gravity will have a negative x component and a negative y component because it's in the third quadrant. And the x component will be based on the cosine of theta because it's adjacent to the angle. And the y component will be based on the sine of theta because that's opposite to the angle. So this will be fg cosine 90 minus theta, fg sine 90 minus theta. So those are my forces components. And now I need to form these with Newton's laws. And remember, Newton's law says that the sum of all the forces for an object which is not accelerating have to add up to 0. So I'm going to compute the sum of forces. The sum of the forces in the x direction is just the x component of the force of gravity plus the x component of the force of friction. And the sum of the forces in the y direction is just the x component of the force of gravity plus, the y component of the force of gravity plus the y component of the normal force. It's worth noting here that cosine of 90 minus theta is the same as sine of theta, and sine of 90 minus theta is the same as cosine of theta. You may have learned about these when you took trigonometry. They're called the cofunction identities. And that allows me to kind of simplify my notation here and just say, okay, this is just sine of theta, and this is just cosine of theta. Okay. Now, Newton's first law says that I should set these equal to 0, and then solve for whatever variable I'm interested in. So, here is the sum of the forces in the x direction set equal to 0. So let me write that here. This is sum of force x equal to 0. This is the sum of the forces in the y direction set equal to 0. And then the bottom equation is just a final solution step. So if we look over here, I start out with the negative force of gravity times sine theta plus the force of friction is equal to 0. And my goal here is going to be to get the sine of theta by itself. So to do that, I'm going to move this to the right-hand side, so you can see it gets moved there. And I'm going to divide by the force of gravity. And so I'm left with the sine of theta is equal to the force of static friction divided by the force of gravity. Next, I'm going to come over to here to the y equation, and I'm going to try and get cosine of theta by itself. So I follow a very similar process. I move this guy to the right, then I divide by the force of gravity, and doing so leaves me with cosine of theta is equal to the normal force divided by the force of gravity. Now, the reason I'm doing this is when you're dealing with trigonometric functions, especially when you're dealing with sine and cosine, which are not independent of each other, it's helpful to isolate sine and cosine and then put them together into a single identity. One function that is particularly useful for this is tangent of theta, because tangent of theta is sine over cosine, so I can kind of combine information about cosine and sine into one equation here by using tangent. Another common identity to use would be the Pythagorean identity. So for instance, cosine squared theta plus sine squared of theta is equal to 1. And so there might be some interesting information that could be found by substituting these guys into there. But I'm not going to do that because I already kind of know where this problem is going. The tangent of theta is sine over cosine. That's a well-known identity. And for this problem, sine of theta is the force of static friction divided by the force of gravity. So we just do a substitution where sine of theta is substituted for that expression. Similarly, for cosine of theta, we substitute the normal force over the force of gravity because of this equation here. Next, you can see that the force of gravity cancels on the top and bottom, leaving me with the force of static friction divided by the normal force. Now I have the tangent of theta is equal to that, so to solve for theta, I need to take the tangent inverse. And so I have my final equation for theta, which is the angle that corresponds to a particular static friction force. Okay. So what this means is basically the static friction force divided by the normal force will determine the angle. Well, there's a relationship between the angle and that amount of friction. That's all I really have to say there. Now, I want to find the largest angle that can be supported based on the coefficient of static friction. And so when I'm looking at this expression, I need to think about how does this depend on the frictional force, okay? And the answer is that because theta is the tangent inverse of this ratio, we need to think about the function tangent inverse. And it turns out that tangent inverse increases monotonically with its argument. And what that means is, if you look at this graph here of tangent inverse of x versus x, as x increases, so does the tangent inverse graph. Okay. Another way of putting it is the derivative of tangent inverse of x with respect to x is greater than 0. Okay. So that means as the input of tangent inverse increases, so does its value. Okay. So if I want to maximize theta, all I have to do is maximize the force of static friction. So doing so, I take theta max by making the force of static friction equal to its maximum value. And of course, the maximum force of static friction is equal to the coefficient of static friction times the normal force. So I just substitute that in there, and now I have mu sub s Fn over Fn, and you can see that the Fn's cancel. And so that leaves me with just mu sub s. So the angle of repose is equal to the tangent inverse of the coefficient of static friction. And so that will determine the largest angle at which you could place this incline and still continue to have the block stay on the incline. So you can actually use this to determine mu sub s for yourself in sort of a home experiment. So you could take like any textbook, okay, and you can place something like maybe an eraser, pencil, a ruler, anything that would just kind of stick on the textbook. And then you can increase that textbook's angle until the eraser starts to slide down. And you've got some measured angle here. And to determine mu sub s, all you would do is you would compute the tangent of that angle. Okay. This is actually a fairly reliable experiment. One thing I would say is that the heavier this object is, the more reliable your results will be, because that'll give you a better signal to noise ratio. Unfortunately, if you have a very light object, the frictional force is very faint and the angle is so tiny that you don't really get a a very numerically robust answer. So the heavier the object, the more of a signal you have to drown out the noise. So that is the inclined plane problem, and there will be a few more problems to follow this one.